guys, for the second part of Unit 4, we're going to look at something specifically called periodic trends. And basically what this means is there are several properties, and we're going to look at three that change as you go across the periodic table and as you go down the periodic table. So we're going to be looking at what those trends are, what the trend is across and down the periodic table, and why those trends are the way they are based on the nucleus of the atom and the number of electrons and things like that. So the first property we're going to focus on is atomic radius. And when we measure the radius of an atom, it's basically how we measure an atom's size. And it depends on, or it's influenced by, the electron configuration. Now, there are two different ways that you can measure the radius of an atom. For metals, the atomic radius is half the distance between adjacent nuclei in a crystal of the element. So if we're looking at the distance between the nuclei, half of that represents the radius. Now, if an element is a nonmetal, which means it occurs in molecules, then the atomic radius is half the distance between the nuclei of identical atoms that are chemically bonded together. So if we have two hydrogens bonded together and their nuclei are 74 picometers apart, then the radius is half of that. So it's a little bit different for metals and nonmetals, but that's really the only way you can truly measure the radius of an atom, because individual atoms don't necessarily have an ending point, so you can't measure them when they're by themselves. Okay, so let's look at our trend. So atomic radius generally decreases from left to right. Now that might seem contradictory to what you would think. As you go from left to right across a period, the mass of the atoms is increasing. They're increasing the number of protons, they're increasing the number of electrons. But what's happening is those valence electrons are being added to the same shell. So there's no more what's called shielding that will affect the attraction between the electrons and the nucleus, because the attraction between the electrons and the nucleus is what determines the size of the atom. The more attraction there is, the more the electrons are drawn to the nucleus, the smaller the radius. So as we go from left to right across the periodic table, the atomic radius generally decreases because we are increasing the positive charge in the nucleus. That means the electrons will be more attracted to the nucleus and the radius actually goes down. Now, it's not a drastic change, but it does decrease as you go from left to right. Now, when we go down the periodic table, we are increasing the number of shells. You're actually adding shells of electrons. So the radius will increase as you go down a group in the periodic table. So if we look at our chart that's given, you can see there's a diagram of the size. So here in the second period, lithium would be the biggest and neon would be the smallest. Even though neon is heavier, we're not talking about mass, we're talking about size. How far are the electrons from the nucleus? So because neon has more protons, then in that second shell, the electrons are more attracted to the nucleus, making a neon atom smaller than the rest of the atoms in the second shell. When you go down to the third shell, it starts over. Sodium would be the biggest, and then it gets smaller as you go across. Then you get bigger with another shell. Potassium is the biggest. It gets smaller as you go across. So on the entire periodic table, where would the absolute smallest radius be? It would be helium because it's on the top right. And the absolute biggest radius would be at the bottom left. Okay, so that is our trend for atomic radius. So let's do an example. Okay, so we want to figure out which has the largest atomic radius: carbon, fluorine, beryllium, or lithium. So looking at the periodic table, we see that all of those elements are in the same period. They have their electrons in the same shell. So the largest radius would be the one to the farthest left with the fewest protons. So of those four, lithium is going to be the one with the largest radius. And if you go back and look at the chart that's in your notes, you can see that in that particular row, in that period, lithium has the largest radius. Okay, now the next thing we want to look at is similar to atomic radius, but now we want to look at the size of the ions. When atoms lose electrons and form positively charged ions, they always become smaller. Okay, now there is a specific name for positively charged ions. We call those particular ions cations. So we're going to spell that C-A-T-I-O-N. Okay, so a positively charged ion is called a cation. All right, so cations are smaller than the original atoms for two reasons. One, they could lose valence electrons and leave an empty outer orbital, meaning the entire thing is smaller. Or, well, not or, and when there are less electrons than protons, there is more electrostatic attraction, not repulsion. There's more electrostatic attraction, so the repulsion decreases, allowing the electrons to be pulled closer to the nucleus. So when an atom loses electrons, it becomes a positively charged cation that is smaller than the atom that it started out as. So you can see down here, sodium loses its one valence electron to have a plus charge, and its radius gets smaller. Now, what happens if an atom gains electrons? Well, then the ion becomes larger. Now, we call negatively charged ions anions. So when an atom gains an electron, it becomes an anion, meaning it has a negative charge. So when chlorine gains an electron, it now has more electrons than protons, so there is actually more repulsion in the electron cloud, and so the atom or the ion is now larger than the atom that it started out as. Okay, so if we look at our trend for ionic radius, as you can see, it's the same as atomic radius. It increases as you go down the periodic table. It decreases as you go from left to right. Now, the only difference is the positive ions decrease, but then around this area, you start getting negative ions. So you can't compare them to each other, but you can compare cation to cation, anion to anion. All right, so let's take a look at our chart on the next slide that's in your notes. Okay, so you can see that here we have our cations getting smaller, 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 and then right about here, right at group 15 and then group 16 down here, that's where we flip over and we start gaining electrons and becoming negatively charged anions. But you can see they still get smaller, smaller, smaller. Okay, so the trend is decrease as you go across from left to right, increase as you go down the periodic table. Okay, now the next trend we're going to look at is a trend called ionization energy. And ionization energy is defined as the energy required to remove an electron from a gaseous atom. So it's basically the energy required to make something an ion, specifically a cation, a positively charged ion. And the energy required to remove the first valence electron is called the first ionization energy. All right, so let's take a look at our graph here. So as you can see in our graph, we have atomic numbers on our x-axis. First ionization energy is plotted on the y-axis. And if you pick a period, let's say from sodium to argon, so that's period 3, you can see generally the ionization energy will go up. Now, there are going to be a few exceptions, which we're not going to worry about, but the general trend across a period is that the ionization energy increases as you go up, go across from left to right. Now, let's look at the next chart that we're given and see what it tells us. Okay. Okay, in our next chart, you can see we have different elements. It tells us how many valence electrons there are. And then it also gives us a bunch of different ionization energies. Now, we talked about the first ionization energy. The second ionization energy is the energy required to remove the second valence electron. The third would be to remove the third, so on and so forth. So as you can see, the number of valence electrons tells us a lot about the first, second, third, fourth ionization energy. So for example, boron has 3 valence electrons. The energy to remove the first one, relatively small, gets a little bigger for the second, gets bigger for the third, but then there's a huge jump from the third to the fourth ionization energy. Well, what that tells us about boron is it has 3 valence electrons, because if we try to remove a fourth electron, now we're trying to remove a core electron, and that electron is way closer to the nucleus and is going to take a whole lot more energy to remove. So when you have a chart like this, you see that big jump is going to tell you how many valence electrons there are in a particular atom. Okay, so let's take a look at our trend for ionization energy. The first ionization energy increases from left to right across a period. Now, why does that happen? Well, as we move from left to right across a period, the radius is getting smaller, meaning the electrons are closer to the nucleus. And the closer the electrons are to the nucleus, the more energy it takes to remove them, because we're having to pull them away from that attraction. And then the first ionization energy decreases down a group because atomic size is increasing, meaning the electrons are farther from the nucleus and less energy is required to remove an electron from that nucleus. So the element with the most ionization energy will be helium because it's the smallest, so it takes the most energy to remove one of its electrons. So up here, this is going to be the highest ionization energy. Down here will be the lowest because the atoms are the biggest and the electrons are the least attracted to the nucleus. Okay, so we're going to pause here, and in the next video we're going to finish up with talking about ions and looking at our third trend, which is electronegativity.